Hello, bonjour, sabajde, zdravo. Welcome to the 5th week of Statistical Mechanics, Algorithms and Computations from the Physics Department of École normale, supérieure. For 4 weeks now, we have concentrated on classical statistical mechanics. And from the equiprobability principle, we have just arrived at the Boltzmann distribution. Time has come to pay a 3-week visit to the world of quantum physics, the world of wave functions and of the Schrödinger equation. We will go even farther into the world of quantum statistical mechanics, where we have at the same time the quantum mechanical wave functions and the Boltzmann distribution of thermal equilibrium. In this lecture, Lecture 5, we introduce to one of the basic models in quantum physics, namely a particle in a harmonic potential, described by energy levels and wave functions that we know exactly. Here is the ground state wave function of the particle at energy equals to 1/2. The square of the wave function gives the probability for the particle to be at position x. And here is the first excited state with energy equals to 3/2. The second excited state with energy 5/2, and so on and so on. Wait a few moments to create all these states by yourself. At a given temperature, these energy levels are subject to the equiprobability principle and to the Boltzmann distribution. In the lecture, in just a few moments, we will discuss exactly how this works. And this will lead us very quickly to the density matrix and the celebrated Feynman path integral that describes the spread of the wave functions through the fluctuations of a path. We all know that at high temperature, the world is not really governed by quantum physics. The essence of our approach to quantum statistical mechanics is a certain transformation called the Trotter decomposition that iteratively brings us from the semi-classical world at high temperatures down to the full quantum world at low temperatures. How this works exactly will be explained in this week's tutorial. We will also discuss the time evolution and program the quantum equivalent of molecular dynamics for simple quantum systems. This week's homework session will again be all about practical computing. You will take your first steps in computing wave functions and in quantum Monte Carlo for the harmonic oscillator. The quantum mechanical harmonic oscillator describes a particle of mass m in a potential 1/2 m omega square x square, governed by a Schrödinger equation. Let us simplify this equation by putting Planck's constant h bar equals to 1, the mass of the particle equals to 1, and the oscillator constant omega also equals to 1. This is not a restriction, and Michael, Alberto, Vivian and I will present the more important equations both with and without the constant. We arrive at the time-independent Schrödinger equation where H is the Hamilton operator or the Hamiltonian. Its solutions, we saw them before, are the ground state wave function of energy 1/2, the first excited state of energy 3/2, the second excited state of energy 5/2, and so on and so on. These wave functions were produced by the program harmonic wave functions.py that implements an exact recursion relationship for the Hermite polynomials. The wave functions are 0 in the limit x going to minus infinity and x going to plus infinity. In addition, they are normalized, which means that the integral from minus infinity to plus infinity of psi n square is equal to 1. Finally, the wave functions are orthogonal. You don't have to believe me that the wave functions computed in harmonic wave functions.py actually solve the Schrödinger equation. You can check this for yourself. To do so, let us rewrite the Schrödinger equation as h psi over psi is equal to E. And let's write a little program, harmonic wave functions check.py, with a discrete approximation for the second derivative. Sure enough, for the ground state wave function psi 0, we find h psi 0 over psi 0 is equal to 1/2 for all x. And for the first excited state, we find h psi 1 over psi 1 equals to 3/2 everywhere. Now let us move right away into quantum statistical mechanics. Quantum means that for a particle in state n, the probability to be at position x is given by the absolute value of psi n of x squared. But we are also doing statistical mechanics. And the probability to be in state n is given by the exponential of minus energy of n divided by kBt, or exponential of minus beta En, where beta is equal to 1 over kB times t. Now let's put the two pieces together, and we find that the probability to be in state n and at position x is proportional to e to the minus beta En times the absolute value of psi n of x squared. Before plunging into this subject, please take a moment to download, run and modify the two programs we discussed in this section. On the Coursera website, you'll find the program harmonic wave functions.py that implements the recursion of the Hermite polynomials. There's also the nice program harmonic wave function check.py that checks that the Schrödinger equation is solved, that the wave functions are normalized and that they are orthogonal. As we discussed a few moments ago, the probability to be in state n and at position x is proportional to e to the minus beta en times psi n of x, psi n star of x. In this equation, the asterisk refers to the complex conjugate. In this lecture and in your homework this week, the wave functions are real valued, so psi n star is equal to psi n. But in this week's tutorial, we have to take into account complex wave functions, so we better use the correct formulas from the beginning. Notice that in these equations we have two different types of probabilities. We have the thermal probability of the Boltzmann distribution and the quantum mechanical probability of the wave functions. Two completely separate worlds meet in this equation. However, the energy levels and the wave functions cannot be computed. And this expression leads nowhere, even for simple problems. To make progress, we discard the information about the energy levels and consider what is called the diagonal density matrix, the probability to be at x, which is proportional to the density matrix rho of x beta equals to the sum over n e to the minus beta en psi n of x, psi n star of x. We also consider a more general object, the non-diagonal density matrix, which is equal to rho of x prime beta equals to the sum over n e to the minus beta en psi n of x, psi n star of x prime. This is the central object of quantum statistical mechanics. For example, the partition function z of beta is given by the trace of the density matrix. As discussed in previous weeks, the partition function z is the sum over the probabilities pi n. But here, the n are no longer positions in space, but the energy levels. We next discuss the three fundamental properties of the density matrix. First of all, each density matrix possesses the convolution property. This means that the integral over x prime of rho of x prime beta 1 multiplied with rho of x prime x double prime beta 2 can be written as an integral over x prime over a double sum over n and m. This can be exchanged into the double sum over n and m over the integral in x prime. The orthogonality property that we just discussed allows us to write this as a sum over n psi n of x e to the minus beta 1 plus beta 2 en times psi n star of x double prime. In other words, the density matrix rho of x double prime at temperature beta 1 plus beta 2. In this exact equation, let us set beta 1 equals to beta 2. The integral over dx prime rho of x prime beta times rho of x prime x double prime beta is equal to the density matrix rho of x double prime at 2 beta. Now realize that beta is equal to 1 over the temperature. So in this equation, we compute the density matrix at 2 beta, that means at low temperature, through a product over density matrix at high temperature. We can use this equation, if we know the density matrix at high temperature, to compute it at twice lower temperature. Then we can use it again to compute it at 4 times lower temperature, 8 times lower temperature, and so on, until we reach the full quantum regime. The second property is the free density matrix. We will derive this equation at the beginning of this week's tutorial and make sure that you understand the role of the non-diagonal elements in this density matrix. And we'll illustrate this in nice pictures of the entire density matrix at high temperature and at lower and lower temperatures. As beta becomes larger, the variance of the Gaussian becomes larger and the system becomes more and more quantum. Finally, the third property of the density matrix concerns the high temperature limit. For a Hamiltonian, H equals to H3 plus a potential V, the density matrix at small beta, high temperature, is given by rho of x prime beta is equal to e to the minus v of x over 2 times beta times the free density matrix of x prime beta times e to the minus beta over 2 v of x prime. So you see, at high temperature, the correction of the density matrix to the free density matrix is given by a simple Boltzmann factor e to the minus beta v split into half between x and x prime. But notice that through this expression we have an explicit formula for the density matrix rho of x prime beta without solving the Schrödinger equation for any potential. So this is a matrix. It is the density matrix at high temperature small beta. So now let us invoke the convolution property, and from this density matrix at temperature beta, let's compute it at temperature 2 beta, inverse temperature 4 beta, 8 beta, 16 beta, and so on. We can reach the full quantum regime. Please take a moment to download and to run this program as written for the harmonic oscillator. You can then modify it for other potentials by just changing an exponential factor, not by solving a new Schrödinger equation. We will pursue this great story in this week's homework session. In matrix squaring, the subject of the last section, we convoluted two density matrices at temperature T to obtain a new density matrix at temperature T over 2. By iterating this process, we could go to lower and lower temperatures, starting from the high temperature quasi-classical limit. Normally, however, we cannot do this matrix squaring analytically. For a larger number of particles, we soon run out of space to store a reasonable discretized approximation of rho x prime beta on the computer. So we cannot do the matrix squaring numerically either. We now see how the Feynman path integral overcomes this problem, how it leads to the use of Monte Carlo methods and to the idea of path sampling. Instead of evaluating the convolution integrals one after the other, as we did in matrix squaring, let us write them out all together. So we write the density matrix rho of x prime beta as an integral over dx double prime rho of x double prime beta over 2 rho x double prime x prime beta over 2. Each of the density matrices at beta over 2 can be written as an integral over two density matrices at temperature beta over 4. This gives an integral over dx double prime, x triple prime, x quadruple prime of rho on temperature beta over 4, beta over 4, beta over 4, and beta over 4. Now, each of the density matrices at beta over 4 can again be written as a product over two density matrices at beta over 8. And this would lead us to multiple integrals over x quintuple prime, 6 tuple prime, 7 tuple prime, and 8 tuple prime. The idea we are pursuing is great, but we are having a notational nightmare. Let us write x0, x1, x2, x3, and so on, instead of the cumbersome x prime, x double prime, x triple prime, x quadruple prime, and so on. This gives that the density matrix rho at x0, xn beta is given by the integral over x1, x2, and so on up to xn minus 1 of rho x0, x1 beta over n, rho of x1, x2 beta over n, and so on until rho of xn minus 1 xn beta over n. For the partition function, which is the trace of the density matrix as we discussed before, we find that z is equal to the integral over x0, x1, xn minus 1. So we have one more integral of rho of x0, x1 beta over n, rho of x1, x2 beta over n, up to rho of xn minus 1 x0 beta over n. The variables x0, x1, x2 up to xn in these integrals is called a path. And we can imagine the variable xk to be at position k times beta over n of an imaginary time variable tau that goes from 0 to beta in little steps of delta tau, which is equal to beta over n. Density matrices and partition functions can thus be expressed as multiple integrals over path variables, so-called path integrals. In Markov chain Monte Carlo, we can move from one path configuration to the next by choosing one position xk and by making a little displacement delta x that can be positive or negative. We compute the weight after the move and before the move and accept this move with the metropolis acceptance probability. Note that we can also move x0, which is between x1 and xn minus 1, so that the path will move as a whole. Configurations of a Markov chain simulation for the harmonic oscillator are shown here. The histogram of the x position in this simulation gives the probability of the particle to be at position x, or in other words, the density matrix rho of x, x, beta, the diagonal density matrix. In Python, this gives the program naive harmonic path.py that I ask you to download and to run from the Coursera website. You will modify this program in this week's homework, where you will do your own first Markov chain Monte Carlo simulation of a quantum system or a path integral Monte Carlo simulation. In conclusion, we have plunged in this session of statistical mechanics, algorithms and computations into the world of quantum physics and quantum statistical mechanics. What I've shown you, the case of the harmonic oscillator, can be greatly generalized, as we will see in the coming weeks. The solution of the Schrödinger equation needs a new technique for each potential. And the Feynman path integral is more general. It's for this reason that it is so famous. It naturally leads to the idea of Monte Carlo simulation and path integral Monte Carlo algorithms. As we are becoming to be great experts in Monte Carlo simulations, of course, this approach is just for us. So, as I said, the story will continue to unfold in homeworks, lectures and tutorials, and I hope to keep up your interest in this fascinating subject. Finally, let me thank you for your attention and see you again in further sessions of this lecture course.